So, moving on to the first real and sort of new topic or thing that we need to talk about, and that is to consider the ideal voltage source. So really, think what happens, my question, what happens is, you've got your lights on in your car with the engine off, you start the engine, what happens to the lights? Any idea why? He's got a brand new special car, have he? Yeah. I expect the lights would still go dim when you actually try to start the engine with them. Certainly, if they're filament lamps, they would. I don't know about the modern headlights. But anyway, the natural thing. Sorry. Yeah. The battery isn't ideal, and you're drawing a lot of current for the starter motor, and therefore there's less available for the lights. So it's not an ideal current or voltage source. Ideally, if we had an ideal voltage source, okay, it would supply, in this case, 10 volts, regardless of what current we drew from it. So whether we drew 1 amp or 1,000,000 amps, it'd still give us 10 volts. That would be ideal. And so if that's going to be ideal, then we've got a source here with no other resistance involved in it. There is its terminals 1 and 2, and it will always give me 10 volts to the load, regardless of what the value of that load is and what current it's going to draw. So that would be an ideal voltage source. Its internal resistance, looking into the terminals there, is 0. It doesn't have any resistance. Because if there was a resistance involved in there, when we put some current through it, we'd drop or lose some voltage across it. But this is ideal. And you must remember that. That's an important thing for you to remember. An ideal voltage source has 0 resistance, or a short circuit. Okay, so for any value of load RL, we would achieve the same output voltage from that source. In real life, that is unachievable. So we have a method whereby we can represent a real voltage source. So here's our terminals 1 and 2 we talked about before. Okay. But what we included in the circuit now is a resistor to represent the internal resistance of the source. It's in series with the voltage source itself. So what we've got is, we've got an ideal voltage source that has 0 ohms resistance in series with a resistor RS, the internal resistance of the real source. Yeah? So we've got an ideal voltage source VS in series with its internal resistance RS. When that circuit is open circuit, no load connected as it is now, what's the terminal voltage going to be? What would I measure? Oh, what did I move that? What would I measure if I put a voltmeter across the two terminals there? We've got no load on it. So what's the volt drop across RS? What's the current? What's the current flowing in that circuit at this moment in time with no load connected? no current. We've got an open circuit. Current cannot flow around an open circuit. So, if there's no current flowing here, 0 amps, what's the volt drop across RS? If we apply Ohm's law to RS, that voltage there is I times R, is it not? Yeah? 0 times whatever the value of RS is 0. Okay? So if this is 20 volts, we're dropping nothing across there. What we're dropping across the two terminals to comply with Kirchhoff's voltage law. But these two add up to that. That's nothing. So if that's going to equal that, it must be 20 volts. So open circuit, the terminal voltage of that source is equal to the voltage of the ideal voltage source. Okay? So open circuit, it equals the 20 volts or 30 volts that it's specified. However, when we draw a current from that, we're then going to drop some voltage across the internal resistance, and we'll lose some terminal voltage. Okay, so there's a circuit there. If the open circuit voltage of a battery is 12 volts, so open circuit is 12 volts, i.e. this source, ideal voltage source, must be for 12 volts. Right? And the internal resistance is 0.5 ohms. Find the terminal voltage of the battery when the currents of 2 amps, 20 amps and 80 amps are drawn from it. So what we're saying is we're going to connect a load RL, 3 different loads. One of them is going to draw 2 amps, one's going to draw 20, the other's going to draw 80. What's the terminal voltage under those conditions? See if you can calculate that, please. Right, so what we're doing here, gents, is we're saying how does this voltage here vary as the current we draw from this source increases. Yeah. So at 2 amps, how have you done this? I'll call that VRS. I want something better to call it. Yeah? How have you done it? Yeah, so VRS is I times RS. It's 2 times 0.5 equals 1 volt. Therefore, terminal voltage, we'll call it VT, is 12 minus 1, 11 volts. Yeah? So as soon as we start to draw some current, we lose some terminal voltage. Okay? At 20 amps, VRS is still I times RS, but it's 20 times 0.5 equals 10 volts. So at that, the terminal voltage is 12 minus 10, equals 2 volts. So drawing 20 amps means our terminal voltage drops. Most of our power is being dissipated by the internal resistance of the source. That generator or whatever it is getting hot because we're drawing more current from it. Or your car battery, the load is higher. It's going to dissipate more power across its internal parts and resistance, and therefore give less to the load. At 80 amps, VRS is still IRS, 0.5 times 80, 40 volts. What do you think about that? Because now, when we do 12 minus 40, you get a negative voltage. That's showing there's a limit to this source that it won't go beyond. Will not deliver that current. Okay. What is the limit? Can you work it out? What limit would give us effectively 0 terminal voltage? In theory, because that can't actually happen, because if no current flows, we don't get the volt drop across VRS. So in actual fact, that can't happen. But sorry, how could we calculate it? It's what current gives us. You are right. It's what current will give me 12 volts drop across there, which is 24 amps. Yeah. And in fact, you couldn't actually reach that, because as soon as 0 current is flowing, there is no voltage there again, and therefore to be back to theoretical 12 volts terminal voltage. So that can't actually happen, and you're gonna ruin the source before that happens anyway. So it's only in theory. Okay. So just to recap, the main points of this are that an ideal voltage source should be considered to have 0 resistance, and you need to remember that. And then we can represent a real voltage source by connecting a series resistor to represent the internal resistance of that source. That's then representing the internal volt drop on that source. And any power supply, unless you do something about it, will drop terminal voltage when you load it. Okay, you can get power supplies that will give you a constant voltage, but what they're doing is they're using internal electronics to sense what the terminal voltage is and vary the source inside to keep a constant voltage. You can also have constant current sources. What you absolutely can't have is a constant current and voltage source. It's not possible with varying load. Okay? It is possible to create a power supply that will hold a constant voltage even though the current is changing. The national grid is one of them. Okay? But they have to do something about making sure through the control systems that they vary something else to make sure that we hold a stable voltage. Okay. The only thing they can vary actually is what's called the excitation of the generator. So they use the generator set down at Sizewell is not a permanent magnet generator. It uses a DC current in the rotor so that you've got a variable magnet, because they can't change the speed, because then the frequency would change. And they can't change what the 3 variables are: the strength of the field, the speed that you cut the magnetic field, and the number of turns on the generator. Not too much chance of changing the number of turns on the stator while it's running. Can't change the speed because the frequency will change. So the only thing they can change is the strength of the magnetic field. So they control the magnetic field by varying what's called the excitation current on the rotor. It's quite, yeah. Yeah, I mean, yeah, if you think of it in terms of this model, you are varying the internal resistance, yeah. Right. Moving on then to the concept of an ideal current source. Okay. So symbol for current source is like this one here, two interlinking circles. It's got an arrow showing which direction the current's going in, and the size of the current is specified. Okay. In terms of an ideal current source, if we could have one, it would deliver the same current regardless of what load we connected to it and regardless of what the terminal voltage was. Effectively, what we're saying here is that an ideal current source has an infinite internal resistance. It just delivers current, but no current is lost inside it. There is no parallel path for current to go. All the 2 amps always goes through the load, regardless of the value of the load. And the constant current is a little bit more difficult to get because that's a little bit harder to imagine how a current source could be ideal in the real life anyway. Okay. The voltage source is definitely easier to understand. Okay, but we can represent what happens with a real current source by representing it as an ideal current source whose resistance is infinite in parallel with its internal resistance source. So this time there's a parallel resistance. So these are the 2 terminals 1 and 2 of that real current source, which is an ideal current source, and its parallel resistance. So now we've got a load connected. Some of the current, the 2 amps, will go through the load, IL. Some of it is lost inside the source, inside the real source. And that loss is represented by saying it's got a parallel path. So some of that 2 amps is just going to go round and round inside the supply, and some of it's going to go through RL. What is also going to happen in that circuit is that the terminal voltage is going to change, because ultimately that current source is provided by a source of voltage anyway. It's just that we're interested in its current value rather than its voltage value in some circuits. Okay. So if the terminals are open circuit, we take the load away. If we was to take this load away, all the 2 amps in this case flow inside there. When we connect a load, some of it comes this way, some of it goes through there. Yeah. So the terminal voltage is varies with load. All right. Understand. So when a terminal is open circuit, current I passes through the internal resistance. Should be noted that this is a representation of the current source that represents how a real one would behave under load. Yeah. So, quick example An ideal current source of 4 amps has an internal resistance of 60 ohms. Find the load current and the terminal voltage when a load current is A 20 amps and B 150 A 20 ohms and B 150 ohms. So how are we going to do that? 4 amps, initially 20 ohms, sorry, that's 60 ohms, always. When this is 20 ohms, how are we going to find the load current and the terminal voltage? It's a method. Yeah, possibly. From the information you got there, Joe, what can you calculate? Yeah, you could do. What, directly? Give me a formula for it. Yep, yep. So you could find RT, can't you? It is RS, RL over RS plus RL. So you can find that. And then so from that, you can use Ohm's law to find the terminal voltage, because that 4 amps is going, some of it's going there, some of it's going there, but all of it is going through what is effectively RT, isn't it? So we can use that to find the total voltage. I, call that I, the total voltage, IT if you like, times RT. Then how can we find the current RIL? Because that's what we're interested in mainly, is how much of that current travels through there, using what we've already done. We now determined, we've found that, we know what that is, so therefore we can use Ohm's law, can we not? Find IL is the terminal voltage divided by the load resistance. So with any problem, it's about what information have I got, what extra information can I find from the information I've been given, and breaking the problem down. So Kirchhoff's law didn't come into it, okay, but it's possible that it could have done if you chose a slightly different method. But in this case it didn't. Okay. There's a current divider rule we could have used, but we haven't. Yes, Mark. No, because that's the ideal current source. That delivers 4 amps. This is the internal resistance of that source. So when there's always going to be some current, IS, flowing down there. But depending on the value of this, that current's going to vary. So you're going to lose some inside the thing just going round and round. And some of it is going to go through the load. And that will vary dependent upon the value of load you connect. I mean, if the load resistance is high, less current's going to go through there, more of it's going to go down the parallel. Yeah. Alright. So that are the results you should get for 20 ohms and 150 ohms. So as you can see, with regard to the load current, if we increase the resistance of the load, less current will go through the load, therefore we must be losing more inside the supply. Yeah, for a current. If we consider it in terms of a current source. Okay? And the terminal voltage, if we're gonna, the terminal voltage is going to vary to allow that to happen. Again, if we load up, the highest load is where the most current's being drawn, remember. High load, low voltage, lower load, higher voltage. Don't think in terms of more resistance as higher load, less resistance as higher load. It's going to draw more current if the resistance is less. Okay, we'll pause there